Hello guys, thanks for coming. It is a pleasure to be part of DevClub family. So it will be my first time to speak publicly in front of a lot of people. So please bear with me. So let's get started. Today I'm going to talk about how we used streaming data processing with Apache Kafka and Apache Flink. But before we start, let me ask this question. How many of you using Kafka?
Every day.
At home.
Cool. How many of you using Kafka in production? Okay. Thank you. How many of you knows what does it mean unclean leader election in Kafka? Okay, cool. And let me ask another question. How many of you guys knows something about Apache Flink? Okay. How many of you use Apache Flink in production? Okay, looks like not so much. Yeah, okay, let's do it. So, about Ness. We are a global company, we have 11 innovation hubs, and we do have nice office in Riga as well. So, we have plenty of strategic partners, including AWS and Confluent. So, and about me, so I'm an engineer, so my passion is writing data-intensive application, conducting different performance tests. We have Apache Flink University business, and where I'm instructor. Also, I'm Confluent Apache Kafka certified developer. Actually, I passed my certification twice. Yeah, let's get started. Today, our agenda will be this case. So, it's about a real client case and how we tackled the issue with using data stream technologies. Let's talk about client case. So we are talking about Instinet company. So Instinet provides global trading platform. So we are talking about around 1 terabyte data daily. We are talking about 200 million messages daily, sometimes more, so it depends. And it's multi-region trades, so Instinet has different regions like US, Europe, and Asia. And prerequisites. So originally, client was using this architecture, which was deployed on their own private data center. So, and we have blend server. Blend server stores trade sessions, and those sessions contains different type events, including order, quotes, etc. So, message from blend server has binary format, and message size approximately 256 bytes, something like this. Loader does some transformation, enrichment. We are talking about ETL process, and loader has a state. So basically, it keeps some messages. So in this particular case, it keeps those messages in memory. It does some calculation. So we are talking about stateful data processing, and then I would say it's important that message sequence is important, and message processing should be organized in order. So there is no way to break order. And ultimately, loader inserts a calculation result of MySQL onto different tables, MySQL sites. And let's have a talk about advantages and disadvantages such kind of architecture. So obviously, it's not horizontally scalable. So it's limited by one instance. Of course, you could add more cores to it, and so on. But initially, this is what client used. So loader has complicated logic for parallelization, so it's required hands-on experience with multi-threading programming. So we are talking about threads, thread pools, synchronization, atomic, and so on, blocking stuff and so on. So it's hard to maintain. Sometimes it had some wrong calculations, so bugs, race conditions, and so on. And performance wasn't really great. So we are talking about like latency around 15 seconds, and throughput, insertion throughput into MySQL was around 60,000 pages per second. And a loader keeps state in memory. In case of failure, it rereads entire session from blend server, so it's not great. And the client should spend a lot of time just to get required data on MySQL side. So as an advantage, state keeps in memory, it's very fast, data accessible from multiple threads. Of course, you need to take into account synchronization to those data, but it's feasible at least. And now client asks, can you make it work faster? Can we have, let's say, 120K messages per second with lower latency? So can you make it more maintainable? Can you make it predictable, scalable, fault tolerant, and so on? So our proposal was about migrate current client solution to new architecture with using power of AWS cloud. So we should improve performance, reduce IT operation costs, make it to be horizontally scalable, more maintainable, reliable, automatically recoverable from failures. And this is why we decided to leverage all those technologies. So we decided to use AWS MSK because it's fully managed service from AWS. So we're talking about Kafka service. And we decided to use Apache Flink. Luckily, we have AWS KDA, which also fully managed service by cloud. And just to eliminate bottleneck with database, we decided to use Aurora, which has a compatible interface with MySQL, and it scales pretty well. And we have to keep compatibility with current Instinet clients, so we couldn't change everything. So that's why we had to stick with MySQL compatibility. Now let's have a talk about why we decided to use Apache Kafka. So first of all, we are talking about open source. So right. So it is really fast. So Kafka designed to handle 1,000 messages per second with low latency. So we are talking about almost near time real data processing, and it's designed to handle a lot of amount of data. So it scales very well. So thanks to partitions, we could create topic, we could provide our partitions, and all these partitions will be distributed across your Kafka broker cluster. So it's fault tolerant. So thanks to partition replication, we could provide how many replication replicas we need. So, and Kafka will handle all the stuff for us. So it allows to decouple data producer and data consumers. They work independently in a synchronous fashion, could be updated independently, and so on. So it's very cool things. Kafka out of the box has ability to reply events. So if you notice that you introduced bug, so you could return back and reread data which you have in Kafka. So essentially Kafka is just distributed log, right? So you could reply your events and produce correct results. So it supports multiple consumers. So you could consume data with different consumers groups, with different level of parallelism. It's totally fine for Kafka. So why we decided to use Apache Flink? So first of all, we are talking about fast and correct ETL. So your payload can be literally, we are talking about highest throughput, low latency, so that's fine. It's distributed and scalable. So Flink has nice parallelization model, so you could run your computations on thousands of cores, so it's totally fine. It has notion of state, so basically your data processing could be stateless and stateful. This is what we actually need. So it has pretty nice data flow programming model. So it's similar like Java Stream API that we got from Java 8. So it has notion of source and sink functions. So basically, this is where you can get data, transform your data, and output data. And as a source and sink functions, it could be not only Kafka. So if you're familiar with Kafka streams, for example, only supports source and sink within Kafka. And then you have to introduce Kafka connectors and then put your data into external third-party systems. So Flink has notion of fault tolerance thanks to checkpoints, sensitive points, so we will cover it. It has very informative UI. So basically, when you deploy your pipeline, you could go into Flink UI and see how it looks like, what is going on, and so on. We will cover it later. So, and I would say it's de facto global standard for data streaming computing nowadays. So, and it has beautiful logo, right? So if we compare Apache Flink with Hadoop, Hive, so they look colorable, but look how beautiful it is.
Main reason.
Yeah. So, the most basic knowledge about Flink. When pipeline executed, Flink programs are mapped to streaming data flow. So it's consisting of streams and transformation operation. So operators could be stateful or stateless, and each data flow starts with one or more sources and ends in one or more things. So the data flow resemble arbitrarily directed acyclic graphs back, and you can have different level parallelism per each operator. So basically has notion source functions, process functions, sink, and Flink creates distributed representation of this data flow graph. So basically we read data, we do kind of map reduce stuff, and then we sync those data into some external things like database, I don't know, Elasticsearch, S3, whatever. So Flink has different options for storing state. It could be in memory or on disk based. So as we discussed, state is fault tolerant, and Flink has notion of checkpoint. So basically, checkpoint in Flink is a global asynchronous snapshot of application state that's taken on a regular interval and sent to durable storage like S3, HDFS, and whatever. So in case of failure, Flink restarts an application using the most recently completed checkpoint as a starting point. Let's have a talk about Flink parallelization model. So basically, here is a Flink cluster. Flink has notion of task manager. So task managers are responsible for running tasks. So it's kind of working guys who execute your tasks. So each task manager runs inside JVM process. You could have different numbers of task managers, like 0, 1, or whatever, inside your Flink cluster. And it has notions of task slot. And the idea of task slots is to slice the available resources up to smaller parts. So in each slot you can deploy one or more tasks. And each task executed by dedicated thread. We are talking about just Java thread. So those you can have multiple threads running in the same slots if you have multiple tasks deployed to it. And task represents a parallel instance of a single Flink operator. So basically, the total number of slots is your level of parallelism. So in this case, we have maximum level of parallelism 6. And you could have configuration where you could have maximum parallelism level 1000, let's say. And moreover, it's scalable. So it depends on your payload. You could add more task managers, task slots, and after, if you're done with your payload, remove those task slots, and it's totally fine for Flink. Now, this is how our solution, final architecture looks like. So basically, we have Kafka loader. So Kafka loader does subscription and responsible to get events from Blend server. So basically, it's responsible to transfer data from Blend server to Kafka cluster. Then Flink loader reads data from Kafka with some level of parallelism, does ETL, and finally sync reports to AWS Aurora. So AWS Aurora has MySQL compatible interface, so we are okay with existing internet clients. We are using CloudWatch for getting logs, monitoring, alerts triggering, and we decide to use DynamoDB from AWS for keeping different configurations. So this is high level of architecture. And now let's talk about components. So Kafka loader responsible for transfer trade session from Blend server to Apache Kafka cluster. So it distributes, it's responsible for distribute data across Kafka partitions. So in our case, Kafka key is order ID. So we need just shared our data across Kafka partition. So basically, yeah. And also it broadcasts quotes across all available partitions. So since we don't have global storage, so we need to somehow organize it. And we decided to broadcast quotes across all available partitions inside Kafka. So it's fault tolerant because in case of, so it won't reread entire session in case of failure. So because it reads latest messages from Kafka, extract requires session and sequence number. Then it asks blend server to provide those events from those specific position, I would say. And the blend server supports this great cool feature like replying events like Kafka. Nice. We made it highly available, so it means that multiple instances could be running in parallel, and only one instance can be active. So thanks to AWS dynamically distributed clouds. And this is how we do sharding data. So basically, we have Kafka loader has Kafka producer, we got message from blend, so in this case we are talking about order related message, which order has ID. Based on key, Kafka producer calculate corresponding partition and send this message into specific partition. So if you will get another order with the same ID, this message will be sent to the same partition. So this is important. So this is how we achieve preserve sequence of message processing. And of course, on consumer side, you could read data from all those partitions in parallel and be responsible only for data processing for this small part of amount of data. Yeah, and quotes should be globally available. So again, if we got quote, so we just broadcast this message into all available partition, and in this case, Kafka key really doesn't matter. So Kafka is about key value. Yeah. Now let's have a talk about Flink loader. So Flink loader just Apache Flink streaming pipeline. We use data stream API. So it's kind of DSL, very similar to Java 8 as we discussed. By the way, it supports also table API and SQL interface. So you could combine, interpolate your pipeline with those stuff together. So it's totally fine for Flink. So with Flink pipeline, we can read data independently per Kafka partition. So yeah. So on Flink loader side, we filter out data because not all data required to be processed and populated to AWS Aurora. And we use key by, this is cool feature from Flink, just to partition our data across Flink cluster. So as we discussed before, process order, it's stateful processing, we keep state, so sequence, message sequence is important for us. And since we are partition it by partition ID, so partition ID is partition number from Kafka, so in this case we are able to get quotes as well per each subtask. And we use orders and we populate price information. We enrich orders with price information from quotes. And then we route data to different things. It depends on message type, so each message has its own type. And we route this different thing, and sync responsible for deliver this data into AWS Aurora, and it build kind of batches because we need to batch data into Aurora from just to achieve higher throughput. So challenge for us, we need to difficulties we overcame. So since we don't use transactions on Kafka loader, so we are talking about Kafka producer, and we are using at least once delivery semantic, so potentially we could get some duplicates on Kafka, and as a result those duplicates we will get on Flink loader side as well. So to deal with it, we keep in Flink state unique identifiers from message, so we can distinguish if we already processed that particular message or not. So this is place where we used state. So we sync data into around 100 tables, and we should build sync dynamically. Depends on number of tables inside the database. So we just use run some queries against MySQL, collected tables which we're interested in, and based on this, we are building our topology. So we should have different parallelism level for different tables because we need to save some resources. So basically, sessions could contain different message types, and for some table we could have, I don't know, billion of messages. For some table we could have just few messages. There is no reason to build sync for few messages with more than one parallelism. So that's why we decided to keep pipeline parallelism configuration inside AWS DynamoDB. Again, we had to use idempotent writes on MySQL side. So we are talking about upsert, right, semantic. And we used insert on duplicate key. So in case of duplicates, we just update our data and we are idempotent. So other options, because MySQL provides different options for those, we could use replace, but internally it performs delete, then insert data, and the most quickest way it's use insert ignore, but basically it's about like fire and forget, because you will never know if your data was inserted or not. So, but it gives a lot of performance boost, but please don't use it. Be careful with this. We had to identify bottlenecks, so that's why metrics are important. So we had to conduct a performance test. We should conduct capacity planning. You know, on Kafka side we had to calculate number of partitions. So because number of partitions, it's your level of parallelization, right? Oh. You need to know ahead of time how many partitions do you need in Kafka. To be honest, out of the box, open source version of GDB sync wasn't great, and our first numbers was not really great. So we had to fork GDB sync and fix some performance issues. Like for some reason, it enabled after commit true. So, but we are talking about batches. So in this case, the database performance degradation was take place. Yeah, and also we interested in data distribution across Flink subtask, and let's talk about it a little bit. So the important thing about data distribution is that if you got your data distribution more or less evenly, so in this case you will get maximum throughput and the lowest latency. So this is just an example of Flink UI. You could see that we have some operator, it's up and running, it has just full level of parallelism. So we are talking about just 4 subtasks, and number of bytes and records more or less equal. So this is important. Sorry, this is not spider. Don't be afraid. This is how a real Flink pipeline looks like. So this is data flow graph with level of parallelism 64. So unfortunately, it is zoomed out, and it's not possible to see all your graph topology. But in the bottom, you could see those tables from MySQL. And if we zoom in into this pipeline, you could see how data flow graphs looks like with just one level of parallelism. So basically, we read data independently by our Flink loader, which is Apache Flink. So for this, we have Kafka source function. Then we do convert, because we are talking about binary message. So we have to convert it to Podger, then filter out data which we are not interested in, then deduplicate it. So in this case, we are using Flink state. Then we have to enrich our data, because we are talking about orders. So orders should has kind of state machine. So, and then finally we wrote our data into different JDBC sync, and then our data written into AWS Aurora. Metrics, which is let's talk about important metrics which we are using. So basically, first metrics would be consumer log. So basically, we have Kafka producer, we have Kafka consumers, and if you have huge gap between messages which you're not able to consume, you will get some difference, like 2 million messages behind or something like this. So keep your consumer log around 0. In this case, your will be like real-time data stream. What's this? Checkpoint size. So basically, Flink has a state, and you should understand how huge your state. And checkpoint size gives you a hint about your Flink state, and make sure that you understand your numbers. What kind of state do you have? So it's important to monitor checkpoint duration. So it's basically time it took to complete the last checkpoint. So, for example, Kafka source commits the current consuming offsets when checkpoints are completed. So, very important metrics. Number of failure checkpoints. So, in case of failure, you need to know about it. You need to, I don't know, do something with this. Pipeline restarts. So, for some reason, pipeline could be restarted. You have to be aware about it, and reasons could be like, okay, my Kafka source function couldn't connect to Kafka, my JDBC sync function cannot insert data into AWS Aurora, so everything could fail, and we as a developers has to be responsible for all those failures, and it should be designed out of the box from beginning of the project. So, if you are talking about performance characteristics, so Flink out of the box provides throughput. So each operator has in, out, right, interfaces, and you could see how many records per second, how many bytes per second you are currently processing, and you could summarize all these metrics and get your overall throughput and so on. Of course, resource consumption is important, like CPU usage, memory usage, network utilization, and so on. And for us, it was important to see Aurora's throughput, right? Because we are promising to improve our performance. And also, since we are talking about batches, we were very curious about latency, how long we insert those batches into AWS Aurora. Okay, this is what we achieved. As you could see, we got 120K messages per second on Aurora side ultimately, which is pretty nice. And our JDBC batch latency was around average 3.5 seconds, and maximum was around 5.5 seconds. Yeah, and minimum was around 1.5 seconds. Let's have a talk about conclusions. So, is Flink the answer to the ETL problem? Yes, looks so. We achieve what we promise. It is maintainable, fault tolerant, scalable. Let's talk about some disadvantage, what we should take into account. So Kafka loader throughput is limited by amount of quotes. So it's okay to fan out quotes to multiple partitions, but it can't scale infinitely. So let's say with 32 partitions, we can have 200k messages per second. With 64 partitions, we could have 120k messages per second. So basically, our throughput on Kafka loader side, not on Flink side, kind of depends on number of partitions on Kafka. And of course, since we are broadcast quotes, it requires additional Kafka disk space usage. But as a benefit, what we got that we didn't introduce new infrastructure on client side. For example, we could introduce, I don't know, some in-memory database and keep quotes globally, but then you will get another pain how to manage this infrastructure, how to make it fault tolerant, scalable, and so on. So it's kind of trade-off. And again, if you are talking about throughput latency, it's always trade-off. So that's why we played with batches on Aurora side, with different settings. And to be honest, everything was configurable in our pipeline. So basically just by changing some settings in our configuration, we could get completely different pipeline on Flink or in Kafka loader. For example, on Flink side, we could even change our upserts, like to test insert ignore, for example, or test I don't know, replace. So keep in mind that having flexible configuration, very cool stuff. And yes, database still main bottleneck. You know, MySQL out of the box supports InnoDB database engine, and you could change this engine to black hole, and just these changes we got automatically 300k messages per second on our side. But it just proves that Flink is not bottleneck, it can scale infinitely, so we need to deal with Aurora. And yes, the problem was these indexes, these I don't know, different types of columns and so on. And as a like future enhancement, would be nice to have something like this, like NoSQL solution, and report your data into something which more distributed. So, yeah. But it requires some, I don't know, adapters for clients, because clients has to be updated as well. So these links, please use it. I'd love to share all of them with you. And questions?
So I'm not familiar with the operations available, and what kind of constraints do the available operations impose on the algorithms we can perform on Flink? Can it, for example, check if a number is prime, and how efficient would it be?
Basically, we are talking about operations on Flink side, right?
Yes.
Okay, so Flink has a lot of different operations. It's a very simple map, right? When you get your message and do some transformation, and you need different type of message. So if you're talking about even what? Sorry.
Checking if a number is prime.
Okay, checking if number is prime. So we are talking about you could use Java language in those operations. So on Java side, it very simple mass function. If just to check if your number is prime or not. So it's not big deal. So you have to write it by yourself.
It can execute arbitrary Java code.
Sorry?
Can Flink execute arbitrary Java code?
Yes. So basically, you're writing your pipelines with using Java, but your pipelines could be written in Scala or in Kotlin or even in Python. So moreover, it supports now SQL interface. So basically, you could write your Flink pipelines with using like NC, SQL. Yeah.
Okay, thank you.
You mentioned that you had 64 tables on the Aurora side. How many topics did you have?
Sorry?
How many topics did you have?
Topics?
Yeah.
We are talking about just one topic, but this topic on Kafka, we are talking about Kafka, right? This topic had 64 partitions. So it's like our maximum level of realization.
So basically, they were running in parallel, right? So
Yes, yes.
you were not dependent on the sequence of the events.
Well, because we are using Kafka Producer, because we use key on Kafka Producer, then each event which belongs to the same key will be put into the same Kafka partition. So in this case, you will not break your sequence of order, because when we are talking about Kafka, basically Kafka, it's about also key value pairs, and based on key, it gives you opportunity to preserve your sequence and shard your data across Kafka partitions. Moreover, you could write your custom partitioning if you need to, I don't know, to deal with this. My assumption is that next speech will be about mass, how to distribute your payload, but it's just my guess. So, because when we are talking about distributed computing, so data distribution important. So good to know your data as much as possible. Good to know your key cardinality, and essentially, if we are talking about Flink, it was originally invented by people who decided to do not ignore 30 years of experience with writing databases. So basically, they were a little bit disappointed that Hadoop ecosystem didn't take into account all those optimizations which people already had. So that's why they built this interesting toolkit which allows them to parallelize their payload and achieve, I would say, almost real-time data processing. Yeah.
And one more question, how big was this Kafka cluster?
How big Kafka cluster?
I mean, nodes, memory?
Well, we are talking about AWS MSK solution. So I'm not sure about how many brokers we had, maybe 5. Yes, I think yes, 5 brokers.
So you increased your throughput 2 times, so that how many times did the hardware requirements increase? So it's really
good question.
to the
Yes, yes, good question. So basically, first of all, before it was kind of monolithic application, right? It wasn't horizontally scalable at all. Now we just made it to be horizontal scalable, and you could play this. It could be after scalable, so it depends on your payload. You could trigger scaling on AWS KDA side, and basically maximum amount of QPUs which we used on KDA was about 64 QPU. It's kind of CPU, similar to CPU, but this after scaling enable, if you don't have any I don't know, high throughput traffic on Kafka, you could handle your data with just one QPU. Of course, AWS Aurora, it's different story, because you need to plan your capacity, and this is, I would say, most expensive. Yeah. was for us, just to achieve this throughput. Any questions?
Yeah, on one of the slides it was mentioned that it was duration for 4 days, 22 hours. So just to ask how Flink is stable. For example, on a scale of like months, half a year, was it some kind of downtime? Because like usually some kind of solutions, 99.99% sincere, just from your experience.
Yeah, so in this case, as far as I remember, our solution should work whole 1 week without any interruption. So basically we are talking about maintenance period during weekends.
And how big was the batch size?
To be honest, I don't remember, but we are talking about like 1,000, maybe 1,500 records inside one gDB patch. So
So
basically,
it's around, 100 batches per second, right?
yeah, it's around 100, yeah. So, yeah.
Any more questions? Okay, thank you.
Okay, thank you.